Now we are going to solve a frame structure by again using the stiffness method. We already worked on this before. Remember that we have an axially rigid frame and it's under only uniformly distributed load. Now we know that when we just first look at this structure, the first thing that we see, this is a symmetrical structure and it's under the influence of the symmetrical loading. And when we think about the deformed shape, we have a symmetry axis here. So that's the symmetry axis. And if we just try to visualize the deformed shape, so we expect to see a deformed shape like that. Sorry for my drawing, but we know that here at the middle the rotation should be equal to 0. So that's the symmetry axis. We don't see any sway because whatever we see on this side of the symmetry axis, the structure, the loading, or the deformed shape should be exactly the same on the other side. So this means that we don't expect to see any horizontal translation. Plus the other information that we know, if we call this middle point as point D, the rotation at D must be equal to 0. So let's try to analyze this structure. Now there's one option, two ways of solving it. Let's take all the options. Option 1, we can just do a classical solution. In other words, if this is my structure, in this structure, I know that there won't be any translation. So I have a rotation here. This is my first degrees of freedom, theta b, and rotation here, theta c. And I will perform the classical stiffness solution by using 2 degrees of freedom. And at the end of the solution, I expect to see theta b is equal to theta c. That's one approach. The second approach is, let's call it as option 2. Is write down the equivalent structure. As behavior-wise, they behave the same. So at the middle of the structure, there will be translation. So the middle will be free to translate, but at the same time, the rotation must be equal to 0. So in order to show that, I can draw, this is the column, and I will draw just the half of the structure. So I have a fixed roller here. Fixed roller means that the rotation is 0, but this point is free to translate. So I have 1 degrees of freedom here, theta b, and the other degrees of freedom is the translation at the middle. So I can use these two approaches to analyze that structure, but I will just go with the second option. Does it simplify the solution? No, but just I want to show that it will be end up with the same results. Okay, so we will be doing our solution by choosing the second option. Okay, so let's do again the discretization. Let's draw the discrete version of that equivalent structure now. These are my nodes and members. Again, I got 2 members here. This is my first member. Let's call it the first member. This is my second member. And let's show the members' degrees of freedom. So since this is the start node, that will be my first degrees of freedom. Let's call it D2, this is D1, D3, and D4. And for the second member, that would be the first degrees of freedom, D1, D2, D3, and D4. Now let's also show the global or the degrees of freedom that belongs to the whole structure. So we have a rotational degrees of freedom here, let's call it uppercase D1, and a translational degrees of freedom, that's uppercase D2. So basically, in order to analyze that structure, I got two members where I will get their stiffness contributions, and I have 2 degrees of freedoms. Now, after having said that, now we can determine the force vector. Remember that in order to determine the force vector, we do superposition. So that's the original structure, sorry, the equivalent structure. We have uniformly distributed load here, that's a fixed support. So this is equal to no deformation, all degrees of freedoms are equal to 0. So what is the loads? So as a representation, that's the way we show it. We make all the degrees of freedom equal to 0, and we end up with a structure like that. And I have a member load here whose magnitude is 12 kilonewton meters. And we want to calculate the fixed end forces and moments. I got 9 here, 9 here. The shear forces are 18 and 18. So these are all the fixed end forces plus only deformation, where we show the unbalanced forces. So that's the structure, fixed roller here, and the unbalanced forces are as follows. Here I have the up direction 9, this is downward direction 9, 9, and the moments are, sorry, the shear forces should be equal to 18, sorry for that. The moments are equal to 9 kilonewton meters, and this is also 9 kilonewton meters. So by looking at this only deformation case, we write down our force vector, and by looking at the no deformation case, we determine our fixed end force vectors for every member. So the force vector for the whole structure is equal to, the first degrees of freedom is rotation, and the corresponding moment is -9. They are in the opposite direction. The second degrees of freedom is translation, and the corresponding force is -18. They are in the opposite direction. So this is the force vector. And by looking at the no deformation case, I can determine the fixed end force vector for member BC. Fixed is equal to, so while determining the directions, I'm comparing this free body diagram with the directions of the second member. So the first degrees of freedom is shear in the upward direction. I got 18 kilonewtons in the upward direction. So this is 18. Second degrees of freedom moment in counterclockwise, I got 9 in counterclockwise direction. This is 18, and this is -9. The fixed end force vector for the second member, for member BC, is as follows. Now we handled the effect of all the external actions. We have the fixed and force vectors, and we determine all the unbalanced forces. Now let's calculate the response of the structure to possible deformations. So we do it by calculating the stiffness matrix. Again, while determining the stiffness matrix, I will be using the element stiffness matrix that we derived before. And again, if you examine this discrete version of the structure, as you see all the degrees of freedoms, the members' degrees of freedoms and the structure's degrees of freedoms, they are all in the same direction. So if that's the case, I don't have to draw any free body diagram. All I need to do is to figure out the contributions coming from each member to the structural degrees of freedoms and add them up. So let's do it. So case 1, the rotation d1 is equal to 1, but the translation, the second degrees of freedom, is equal to 0. So let's come back to this discrete version. I'm trying to create a unit rotation. So for the first member, I ask this question: how much force to create a unit rotation at the end node? It's the fourth degrees of freedom. So I come to this free body diagram, or this diagram. So D4, this is the fourth. So the contribution coming from the first member to create a unit rotation is equal to 4EI over L. So I can write it. I'm saying that K11 is equal to K44 from the first member plus, let's try to figure out the contribution or the resistance coming from the second member to unit rotation. So it means that the second degrees of freedom must be equal to 1. How much force do I need? It's D2, so I'll be looking at K22. So plus K22 coming from the second member. Now I can determine their magnitudes. So K44 is 4EI over L. L is equal to 3. So this is 4EI over 3 plus the contribution coming from the second member is also 4EI over 3. And the total resistance for the whole structure is equal to 8EI over 3. Now I need to calculate the K21. Now we go back to that figure again. I have a unit rotation D1 and I want to keep the translation D2 equal to 0. So if I come to this free body diagram, D2 is unity and I want to keep D3 equal to 1. So that means that I want to keep, there's 2 is equal to, the second degrees of freedom is equal to unity, and I want to keep the third degrees of freedom equal to 1, and the force required for that is K32, and I don't have any contribution coming from the first member, so K21 is equal to this K32 of the second member, which is this value, or this one, minus 6EI over 9. So we determine all the stiffness coefficients for the first case. Now let's do the same thing for the second case. Case 2. Now the rotation D1 is equal to 0. The translation D2 is equal to 1. So let's first determine K22. again, let's come back to this figure. I want to create a unit translation in D2 direction. The resistance will only come from the second member, and for the second member, I want to create a unit translation in the third degrees of freedom, in the direction of the third degrees of freedom, and the resistance for that is equal to K3 coming from the second member. And if we go to the element stiffness matrix, K33 is equal to 12 EI over L cubed. So that's equal to 12 EI divided by 27. What about K12? So this is uppercase K12. That's equal to, again, I'm looking at this figure, D3 is equal to 1, and I want to keep D2 equal to 0. So that will be equal to D3 is equal to 1, and I want to keep 2 equal to 0. That's again, coming from the second member. If we go to that figure, it's these coefficients. It should be the same as this one. And that's also equal to minus 6 EI divided by 9. Now, as you see, we have the stiffness matrix, we have the force vector. Now we can do the solution. Now I have to write down the equilibrium equations. Remember that equilibrium equations are written in the following form. The structural stiffness matrix multiplied with the unknown degrees of freedom should give me the unbalanced forces. That's the equilibrium condition. The stiffness matrix, let's write it in EI parentheses. EI, I got 8 over 3 minus 6 over 9 minus 6 over 9, and K22 is 12 over 27 multiplied by D1 and D2, and this should give me the unbalanced forces minus 9 and minus 18. And when you solve this thing, we obtain the rotation at B, which is equal to D1, as equal to minus 21.6 over EI, delta D, and that will be equal to D2, and that's equal to minus 72.9 divided by EI. So these are the values of the unknown degrees of freedoms. Now let's recover the membrane forces. So let me erase this portion. So I will just do it for the second member, but for all other members, the procedure is exactly the same. So for the second member, let's member BC. That's the discrete version of that structure. So we calculated the value of D2 and D3, and we know that D1 and D4 is equal to 0. So for this member, the membrane displacements is as follows. D1 is equal to 0, D2 is equal to minus 21.6 divided by EI, D3 is equal to minus 72.9 divided by EI, and D4 is equal to 0. So this is the member end forces. So member end displacements, I'm sorry. And the equation for member end forces is equal to the element stiffness matrix of member BC multiplied by the member end displacements. So this part of the equation represents the moments or member end forces due to deformations only, plus we have to add the forces, the end forces, when we don't have any deformations. So this is actually the fixed end moments and forces. So plus F BC fixed. Now, in order to perform K times U, I have to multiply this matrix with the unit, with the member end displacements. So if you think about it, this row will be multiplied by this column. So I won't be using any of the coefficients in the first column and in the fourth column, but I will be using all the coefficients in the second and the third columns. So I will just calculate these coefficients. That's equal to, it's EI in parentheses, so I don't calculate the coefficients in the first column. Second column, 6 over 9, 4 over 3, minus 6 over 9, 2 over 3. The third column, minus 12.27, minus 6 divided by 9, 12.27 minus 6 divided by 9. Multiplied with 0 minus 21.6 minus 72.9 and 0 multiplied by 1 over EI. So I can erase this part also. Plus the fixed end force vector, which is equal to 18, 9, this is 9, 18, and minus 9. And when you do that calculation, we obtain the member end forces for member BC as equal to 36, 28.80, and 25.2. And if we draw the free body diagram, this is member BC, uniformly distributed load on it. So the shear force is in the upward direction, 36. Moment is in the counterclockwise direction, 28.8. As expected, the shear force at point D is equal to 0, and the moment is 25.2 kilonewton meters. And this is the final result. In the second example, we have a beam that is axially rigid and is supported by an inclined truss member. And for simplicity, let's assume that, or let's say that EA of the truss is equal to EI of the beam in magnitude. So that's the structure that we want to analyze. Okay, so let's do discretization so that this way we can better understand how this structure behaves, how we can analyze this structure in the most simplest way. Now, I have a member here. Let's give some labels. This is A, point A, say this is point B, point C, and that's point D. So this is the first member. I have a node here, a cantilever portion, and then we have a truss member. Now, regarding this cantilever, remember that it doesn't matter how much deflection we get at the end of this cantilever. The forces, the end forces, should always be the same, because that's actually within itself, it's a determinate structure. So all end forces are known. So if that's the case, if I know all the end forces, I don't have to worry about the deflections at this end, because it doesn't matter. It doesn't matter what deflections I have. The forces here is always the same. So actually, I don't have to worry about this cantilever and the node at the end of the cantilever. So the structural degrees of freedoms for me is the translation, that D1. Let me erase this thing or rewrite one more time. Sorry for that. So that's node B. So I have a translation degrees of freedom, D1, and the rotational degrees of freedom, D2. Again, as I said, I don't have to worry about the degrees of freedoms at this node, because I don't have to calculate them. I can still write down the equilibrium equations for this node without knowing their values. So that would simplify my solution. So in that solution, I will consider only these two members. That's my first member. That's my second member, which is a truss member. And let's show their local degrees of freedoms. I'll use a different color for that. Start node, translation D1, rotation D2, translation D3, rotation D4, and the second, this is the first member, let's write it down. This is the second member, and it's a truss member, and I got D1 and D2 here. So these are all degrees of freedoms that I have. Again, as I said, I don't worry about the cantilever part. I will only consider the cantilever as a tool to transfer the forces to node B. Now again, forces. Let's handle all the external actions here in determining the unbalanced forces and fixed end forces. So I will not show the truss part because we don't have any force on the truss. We say that that's the structure that I have. That's B, that's C, that's equal to no deformation. All degrees of freedoms are equal to 0, no translation, no rotation at B. Member BC, uniform distributed load. And as I said, the tip of the cantilever is free. This is 15 kilonewton meters, and likewise this is also 15 kilonewton meters. Now for this figure, for this members boundary conditions, let's calculate the fixed end moments. So this is 20, the shear force, this is 30, this is 30, and for the cantilever, that moment is 15 times 2 is the total force, and the moment arm is 1, so this moment will be equal to 30, and the vertical force is also equal to 30 kilonewtons. Plus no deformation case, sorry, only deformation case. Now we will here saying that the unbalanced forces creates nodal deformations, and with the help of the nodal deformations, these unbalanced forces are balanced and the unbalanced forces for this structure, that's point B, is as follows. I got shear forces 30 plus 30 in the upward direction, so I should have the same force but in the downward direction. This is 60 kilonewtons. I have a counterclockwise moment 30, a clockwise moment 20. So here I should have a clockwise moment that's equal to 10 kilonewton meters, so that it will balance the unbalanced forces. So by looking at the only deformation case, I will determine my force vector. So F in that case will be equal to, first degrees of freedom is translation. I got 60 in the opposite direction, minus 60 kilonewton. Second degrees of freedom is rotation, and I got moment in the opposite direction, and I got minus 10 here. So this is the force vector, minus 60 and minus 10. Now again, let's calculate the response of the structure to these 2 degrees of freedoms, and we do it by calculating the stiffness matrix. Let's start from the first case, case 1. Translation is equal to 1, rotation is equal to 0. Now we go back to this discrete version of the structure. So I can directly write the contribution of the first member, because as you see, the directions of the members' degrees of freedom is the same as the directions of the structure's degrees of freedom. But when it comes to the truss member, the degrees of the directions are not the same. So I have to draw the free body diagram and do the geometric rotation of these forces, or calculate the components of these forces, this force in the directions of the structural degrees of freedoms. So let's do that. I no longer draw the cantilever because we know that it has no effect on the stiffness. This is the truss member. K11 creates a unit translation. K21 keeps the rotation equal to 0. So the deformed shape that I see in this member is as follows, right? This is equal to 1. And the deformation that I see in this truss member is as follows. So that's what we see. Now let's calculate the contributions. How much resistance will I get from each member? And if you remember our truss problem solution, the amount of elongation for that truss is this one. So first I have to calculate what this delta is. EA over L delta will give me the force along the truss member. I have to transfer that force to that node and calculate its vertical component, right? So let's write what K11 is first. So K11 from the first member, it is, we are saying that the third degrees of freedom is equal to 1. How much force do I need to create that deformed shape? It is the K33 of the first member. So K33 coming from the first member, plus I want to move that truss member in the upward direction, right, with a unit translation. How much force do I need? So you can calculate it one more time, or you can go back to our truss example problem, because we already derive the stiffness coefficient of a truss member like that who moves in the upward direction. If you go back to that derivation, it's exactly the same situation here. If this, we call that angle alpha, and the force required to create a unit translation in the upward direction is equal to EA divided by the length of the member multiplied by sine square alpha. So there's no need to repeat the same thing over and over again. We already derived that equation in our previous case. So I see the same, exactly the same deformed shape. So the stiffness coefficient should be the same thing. So if we put the values in their places, K33 is equal to 12 EI, length is 4 cubed, plus EA over L. We said that EA truss is equal to EI beam, so I just write EI here. EI divided by the length of the truss member is 5, and the sine alpha is 3/5 squared. Sorry, this should be 5. Okay. Now, when you calculate that, you find that this coefficient is equal to 0.2595 EI. Now K21, so the rotation we don't have an effect, a resistance coming from the truss member for rotation. So the resistance will only come from the first member, and we said that we have a translation in the third direction, and I want to keep the degrees of freedom in the fourth direction, which is the rotation in that case, equal to 0. How much force do I need? That will be K43. It's this one, minus 6 EI over L squared. So that will be minus 6 EI divided by 16, and that's equal to minus 0.375 EI. So we finalized the first case. Now let's take a look at the second case, case 2. So D1 is equal to 0, D2 is equal to 1. Now we have a unit rotation, and we will keep the translation equal to 0, meaning that for the rotation the resistance will come only from the first member. I don't see any resistance coming from the second member, and of course no resistance, no stiffness coming from the cantilever. So since I don't have to worry about the truss, I don't have to draw the free body diagram, so I can just directly say that K22 is equal to K44 of the first member, which is 4 EI over 4. That will give me a value that's equal to EI. And K12, we expected it to be equal to K21, and this will be equal to K34 of the first member, and that's equal to minus 6 EI over 16, and I get minus 0.375 EI. So we have all the coefficients that we need. Now I can perform the solution. So K times U is equal to F. So K is equal to EI 0.2595 minus 0.375 minus 0.375, and diagonal is 1. I have D1 and D2 should be equal to the force vector minus 60 and minus 10. Let me write write this thing one more time. So this should be minus 60. So when you solve that system of equation, we obtain d1 as equal to minus 536.3 divided by EI, and d2 will be equal to minus 211.1 divided by EI, and that will be the final solution. And after that, of course, again the same thing. You have the stiffness matrix here, you know what the end displacements are, multiply the stiffness matrix with the end displacements of member 1, d1, d2 will be equal to 0 in that case, and by looking at this figure, determine the fixed end forces, sum it up with the k times u, you'll get the member end forces for the beam member. So the rest of the procedure is exactly the same. Okay, so that finalizes this question. Now in the following class, we have to find a way to handle this case when the degrees of freedoms of a member doesn't match with the degrees of freedoms of the structural degrees of freedoms. What do we do? That's the question that we will try to analyze. We have to put everything in an automated way so that we can have the computers that do these calculations for us.